Welcome to the Deep Dive. Today we're jumping back to 1949, looking at Hideki Yukawa's Nobel lecture. Our mission is really to unpack, the twists and turns behind his meson theory. It was the first real crack at explaining the strong nuclear force.
It really is a fascinating story. After the neutron was discovered, it became clear pretty quickly that whatever held the nucleus together, it wasn't gravity and it wasn't electromagnetism.
Right, those forces just didn't fit the bill.
Exactly. And Wigner, he showed these nuclear forces had to be incredibly short range, like only working across the nucleus itself.
Which explains why nuclei don't just keep getting bigger and bigger indefinitely.
Precisely. That short range explained the saturation, why the binding energy per particle kind of levels off. The glue only works up close.
So the first thought was, okay, maybe it's related to beta decay. Fermi's theory involved electrons and neutrinos being exchanged.
Yeah, that seemed logical at first, exchanging particles between protons and neutrons, but it fell apart fast.
What was that?
Well, beta decay is, relatively speaking, a slow process. If that mediated the strong force, the calculations showed the force would be way, way too weak. Couldn't hold a nucleus together. They needed something much stronger, much faster acting.
Okay, so that attempt failed. Then in 1935, Yukawa comes along with this gap filler idea.
Yes, a Madsen field.
And the really clever part wasn't just proposing a new particle. He used the known short range of the force to predict the particle's mass.
How did that work? What was the link?
It's this really neat inverse relationship. The shorter the range you need the force to have, the heavier the particle carrying that force must be.
Oh, okay.
So he plugged in that tiny nuclear distance, roughly 10 to the minus 13 centimeters, and calculated the mass needed. It came out to about 200 times the mass of an electron, $200.
Wow, that's incredibly specific for a theoretical particle back then.
It was a bold prediction, and then boom, 1937, cosmic ray experiments find particles.
With intermediate mass. Right around $200.
Exactly. It looked like perfect confirmation. Case closed, right? But it wasn't quite that simple, was it? Physicists started having doubts almost immediately. Why?
Because these cosmic ray particles, while having the right mass, they just didn't act right. They didn't interact strongly with nuclei, which was the whole point of Yukawa's particle.
They were too standoffish.
Kind of, yeah. They interacted very weakly. And the other big thing was their lifetime. They stuck around for about 2 microseconds, $2 times 10 6 seconds.
And that was wrong.
Way too long. Based on the strength needed for the nuclear force, Yukawa's particle should have decayed much, much faster. Calculations suggested something like 10·9 to seconds. A huge discrepancy.
So the mass matched, but the behavior was all wrong. That must have been incredibly confusing.
Absolutely. It led people like Hanakawa, Sakata, and later Marshak and Bethe to think, maybe there isn't just one meson.
The two-meson hypothesis.
Exactly. And Powell's group confirmed it experimentally in 1947. There were actually 2 distinct particles involved.
You can break that down for us.
Right. So first you have the pi-mesons, or panons. These are a bit heavier, maybe 280 meters. These interact strongly. They are the true carriers of the nuclear force Yukawa predicted. They have spin 0.
And the second particle.
Those were the mu-mesons, or muons. Lighter, around 210 meres. These were the ones they were seeing dominate in the cosmic rays at sea level. They interact weakly, have that longer lifetime of $2 times 10 6 seconds, and it turns out they have spin 12, like electrons.
So the pions decay into the nuons.
That's it. The weakly interacting particle they found first was actually the decay product of the true, strongly interacting force carrier.
That is quite an irony. The perfect mass match was for the secondary particle.
A classic case of finding something important, but not quite what you thought you'd found. And even then, the theory needed more tweaks.
Like what?
Well, the initial simplest version of Yukawa's theory, the scalar theory, had problems. It actually predicted the wrong sign for certain nuclear interactions, and it couldn't explain properties like the deuteron's electric quadrupole moment, basically how charge is distributed within it.
So they had to adjust the math.
They did. Switching to what's called a pseudo-scalar field theory fixed those issues, giving the correct signs and shapes for nuclear forces.
And there's also the issue of charge, right? Proton scattering looked very similar to proton-neutron scattering.
Yes. That similarity strongly suggested the force couldn't just be carried by charged mesons swapping back and forth. There had to be a neutral version, too.
So, assumption the 5 in Yukawa's framework, the neutral pi-meson.
Exactly. Predicted to be very unstable because it could decay electromagnetically maybe into 2 photons incredibly fast, like 10-14 seconds or less.
And that was found too.
Confirmed in Berkeley. Right around the time of the Nobel lecture, actually, in 1949.
It's an amazing story of prediction, confusion, refinement, and discovery, packed into just 15 years. So where did Yukawa see things standing in 1949?
Well, despite all this success, he ended his lecture acknowledging that, the theory wasn't complete. There were still these deep mathematical problems, divergence issues, and fundamentally, they still didn't understand the structure of these elementary particles themselves.
So the big takeaway seems to be that even a stunningly successful prediction, like that $200 mass, can sometimes point you towards just one part of a more complex process.
Right. It wasn't the whole story. They found the first link in a chain, not the ultimate source.
It really makes you wonder, doesn't it? When we look for simple force carriers today, how often might we be uncovering just the most obvious stage of a hidden, multi-step interaction?
That's a deep question. It tells us to stay humble, I think, even when our theories seem to score a direct hit. Nature can be subtle.
Definitely something to think about as you explore how forces work in the universe.